speaker couldn't make it, and I decided that we cannot tolerate this void, so I had to step in. This is an excuse because this talk is not well prepared due to this shortness of time. And the first, why relativistic wave packets suddenly? Dirac equation is quite old, almost 90 years old. What has happened recently that this topic became of some interest? Well, it was the set of experiments that were carried out quite recently. They were sort of had high visibility. 4 of the papers were published in Physical Review Letters. And as far as theory goes, all of them were completely wrong. So we decided that it's time to explain to these people what is a relativistic theory of electrons, which is based on the Dirac equation. And the fact is that it's not so simple. Why these people became interested suddenly in electron beams? They were inspired by photon beams. Over the last several years, there was a lot of commotion in optics due to the fact that light is much more complicated than it was believed before. It can have various complicated structures. Some of them are connected with orbital angular momentum, which leads to vortex lines. And there were great experimental achievements in using these optical beams with angular momentum for various purposes. One of them is that angular momentum is how these people like Karol Rzeczkowski call it new resource. New resource, yes. Angular momentum is a new resource because previously one thought that the resource is frequency. That frequency is the main resource which is being sold. Pieces of frequencies are sold to various people who are interested in sending information. And angular momentum is an additional resource because there is a lot of structure which can be used to transmit information. If you have a beam that has high angular momentum, that means that there are many minima and maxima in such a wave, and one can use this to encode information. So that was the reason why people...
How stable are those beams with high photon angular momentum in transmitting? If I have a fiber optic cable via which I have to send information,
cables.
if I send a beam with a very high angular momentum, how often do I have to do something in order to propagate it from Timbuktu to Madagascar?
No, I don't understand. Mostly it's not sent by fibers because fibers are not very good for that because optical fibers are not very good for that purpose. Yes, because because of the structure of waves inside the fiber.
So
and in free space. In free space, they send it from one Canary Island to another Canary Island without, yes, sure.
What about the curvature of the Earth? The Canary Island
Curvature Earth is perfect for that because photons go along the geodesic, so they don't care about the curvature.
Not on the surface of the Earth.
Of course, they always go along the geodesic. That's the property of propagation of light in curved space. Okay, but that takes me away from my main topic. So I will begin now with a brief pedagogical introduction, just to make the rest quite simple. And I will show you how simple the Dirac equation is. So I will produce solutions of the Dirac equation in 5 easy, in 5 easy steps. The first step is, well, everybody. the wire? Yes. I will not break the wire. The first step is something which has the following form: dt squared minus the Laplacian, plus mc over h squared times some function f equals 0, and that is called Klein-Gordon equation. It should have many more names, because not only Klein-Gordon but others at the same time realized that since the Schrödinger equation is just EO equals p squared over 2m plus some potential, so relativistically this relation should be replaced by E squared over c squared plus minus p squared equals mc squared. And this translated into the coordinate space becomes the Klein-Gordon equation. So we start with the Klein-Gordon equation. Then we take this solution. It's a simple one equation only, so it's easier to solve than to solve a set of many coupled equations. So you take the solution of this equation and you form a column, this solution, and here I will call it phi up and phi down is 0, and this I call the spinor, even though you don't need to know much about spinors. This is just a two-dimensional complex vector. Of course, this solution in general can be complex, and that's important. So this is step number 2. I'm sorry, phi of course, phi of u equals f. Now the third step, I define a second spinor, which I call chi, which is defined in the following way. I have...
By the way, this first equation is purely real, therefore f may be...
Of course, it's in general complex, yeah. Complex solutions of this equation are of interest.
Any complex solution is just a combination of two reals.
Well, but in quantum mechanics, it's better not to split them into real and imaginary parts.
But the real part does not interact with imaginary part. So if you really want to split everything into irreducible parts, then you may...
No. That's not the best way to do it. That's what I can certainly say. Because then you lose the whole notion of angular momentum, which plays a significant role. Real and imaginary parts are combined together to produce a wave with angular momentum.
But it's better to say that you take two different solutions.
No, I take one complex solution.
Yeah, and you combine them into...
I don't combine them. From the very beginning, it's easier. I mean, I say, this is supposed to be pedagogical. It's easier never to split this into real and imaginary parts. Now, how do we define this thing here? Well,
Pedagogical is an obscene word nowadays in this country.
okay.
You have to watch it.
This is Compton wavelength. In tech, it's spelled lambda bar. Now I calculate the following derivatives. dt plus dz acting on f. This is the upper part. And here is dx plus I dy acting on f. This is my second spinor, which is again a column of two complex solutions. Again, if I would try to split this into real and imaginary part, it would be a mess. So this is step number 3. So now we have two objects. One two-dimensional vector, second two-dimensional vectors. And I build these vectors. From these vectors, I build now what is called bispinner, which is just a combination of phi and chi. So it has 4 components. And it turns out that this object satisfies the Dirac equation, which is usually written in this form. H here minus mc times psi equals 0. As simple as that, much simpler than to write down, as people do most of the time, the set of coupled equations and then try to solve them. It's much better to go in the opposite direction, just to have something. This could be called the potential for the Dirac wave function, because derivatives of this potential produce the Dirac wave function. Okay, so much for the pedagogical part. And now what we can do with this. Good remark here. Of course, you have to take superpositions, because I only use the upper component. I could also put this in the lower part of the spinner. That would be a different solution, and this will be illustrated in a moment. And of course, every solution of the Dirac equation is built from solutions of Klein-Gordon equations by superposition. These are just very simple building blocks.
If you pass to Fourier transformation, all these manipulations are purely algebraical entities, obvious.
Sure, but
What about the relation between f and psi? These are not the simple derivatives, so there is no
simple.
I can add something.
These are simple partial derivatives.
Oh yeah, but I mean, if I add to the f the one f, which results in the psi something else, which how much of the freedom do I have between f and psi? If it will be a simple derivative, then f plus a constant will be the same function, will lead to the same psi.
Yes, potentials can be modified. There is, one may say, the substitute for gauge invariance. In this case, the gauge invariance is trivial. You can add a constant and that's all. You cannot add something which will be killed later. Like in electromagnetism, there is not much freedom here. Good. So now we...
How can you modify this partial derivatives so that it still makes sense? I mean, it looks...
Why do I have to modify? This is just ordinary partial derivative.
Yes, I mean, but can you modify it in some way so that it doesn't look, I don't know, awful?
Why do I have to modify?
You are using explicitly the basis.
Of course I use Cartesian coordinates.
Yes, but
because this is special theory of
you are
relativity.
using t and z coordinates, for example, right?
So it doesn't look explicitly Lorentz invariant directed this way. So the relation between f and the particular solution of psi is not Lorentz invariant. Both set coordinates.
It would require a brief introduction of spinors, which will make it explicitly Lorentz covariant. However, I don't have time for that. But spinors will solve this problem very nicely. It will show that transformation properties under full Lorentz group are then transparent. Okay, so now we go to something more specific, namely, let me write down the Dirac equation in terms of Pauli matrices, which are familiar to everyone, just to make a better connection. This equation, which is a set of 4 coupled equations, can be written back in terms of phi and chi. Namely, this is where the spinors come in, but they don't have to even be called spinors. These are just two-dimensional vectors, IH, and here is dt plus the gradient and the Pouty matrices acting on phi produce MC chi, and symmetrically IH dt minus.
You have the equations on the board.
Oh, good.
And it's even better. It's better to do correctly.
Yes. These are the equations which, as Professor Tursky noticed, happen to be on my slide, are quite nice because they're symmetrical and they show how these two separate objects are coupled by the mass. If mass is zero, which never happens because even neutrinos have some kind of a mass, then of course these equations would split into two independent equations. Each of them would be called the Weyl equation. Now we can do something with this introduction. Namely, let's take some nice scalar solutions of the Klein-Gordon equation. And the simplest solution that has something to do with angular momentum is one built from Bessel functions. And here is an illustration of what I said before about splitting this into real and imaginary parts. That would be highly complicated because you would have some cosines, sines, and you will lose the physical content of this. Why one would lose the physical content? Because it's this factor here, e to the IL phi, which tells us that there is angular momentum, orbital angular momentum carried by this wave. And these people who did experiments were very much interested in orbital angular momentum. And of course we know that when there is orbital angular momentum, Bessel functions come in immediately. And this is of course a monochromatic wave, but it's highly unphysical because it carries infinite energy, because Bessel functions don't fall off sufficiently fast to give finite energy to such a wave. Therefore, how people who are trying to use this in experiments, they say, well, we are interested in what happens close to the axis of this, and close to the axis we don't care what happens far from the axis. Well, P transverse, of course, is the momentum connected with the perpendicular direction. And as I said, beams. So what was done in optics to make these beams better? Well, we have something in optics which is called Laguerre-Gauss beams. And Laguerre-Gauss beams that were used to interpret these experiments were non-relativistic, even though electrons were 300 keV. So 300 keV is halfway to the rest mass, even more than halfway to rest mass, so one should treat this relativistically. Now, why do I talk about non-relativistic then? Because I want to stress a very big difference between non-relativistic description and relativistic description. One of the important reasons why this description is different is that in non-relativistic Schrödinger equation physics, there is no scale. The scale is introduced when we introduce the speed of light, and then we form the Compton wavelength, which is a parameter, has the dimension of length, of course, and this provides a natural scale, and the scale plays an important role in the properties of the solutions. So what do we see here? This Laguerre-Gauss beam is non-relativistic, it means that it satisfies the Schrödinger equation, the non-relativistic Schrödinger equation. What are the main ingredients of this? Laguerre-Gauss beams are used in optics for like 20 years, and many experiments are interpreted in terms of these Laguerre-Gauss beams. Of course, in optics, Laguerre-Gauss beam looks a bit different because there's no mass here, and the solution in the form of Laguerre-Gauss beams is a solution of the wave equation. And here we have again this important factor e to the I L phi, and these are Laguerre polynomials here, and there is an exponential factor which contains rho in the exponent, therefore it falls off very fast, and this is why it was used to interpret experiments which do not have the weakness of Bessel beams. Now A of t defines the width of the beam, because if W is big, then of course the beam is shrunk to a smaller size. Now, as you see here, beam propagates in the z direction with momentum pz, and this is the common factor in non-relativistic physics, the phase depending on time. So that much for the non-relativistic Laguerre-Gauss beam, which I just use only to connect with something that has been done before. And now we proceed to relativistic beams, and this is something which is not trivial, and it has some properties which are not very nice, even though people who did experiments with electrons did not notice because they were using the non-relativistic description. What is not nice about the relativistic Laguerre-Gauss beams? The dependence on time is in two places. It's through t minus and through t plus. T plus and t minus are just these combinations of time and z. And we know very well from elementary physics, when this is t minus z, then the wave proceeds in the positive direction. When it's t minus z, the wave proceeds in the opposite direction. Therefore, this nice solution of the Klein-Gordon equation is unphysical because it describes two waves, and you cannot split this. There is no way of splitting it in a non-trivial way. Of course, you can separate this into plane waves, and you will see that some plane waves go forward and some of them go backwards. That, however, will not be Laguerre-Gauss beam. So relativistic, needless to say that, of course, when c goes to infinity, one can show that with some problems, one has to remove, of course, the fast phase, the fast oscillating phase. In the relativistic,
the previous one was a solution of
Schrödinger, ordinary
This one?
Klein-Gordon. This is the Klein-Gordon solution, which is a close counterpart of the Laguerre-Gauss beam in non-relativistic physics, and it must have this unpleasant feature.
How does the solution look like? How does it propagate? Are there just two ones which are
This is how it's written on the blackboard. I mean,
yes,
this is.
Yes, but how? I mean,
It has, of course, angular momentum. It has orbital angular momentum because of this factor. And it has these phases here, and it falls off exponentially at large distances. Again, this is interesting. The fall off here depends on one of these times, and this factor here contains.
if you could, I don't know, plot how does it look like along the z-axis in few minutes of time? What's the problem?
What can I say more than what is
That's the solution.
here?
Yes, I know.
Difficult to imagine realization.
Because if I could see the function
this is not an eigenfunction of momentum in the z direction like it was here, and that is why there will be a distortion. When you go along the beam, there is a distortion. It's not a plane wave in the z direction, because the dependence on z occurs here, and occurs here, and occurs here. So you can plot it, and you can see basically what happens here, and that can be seen from here. The waist of this wave, which is defined by a of t, has a minimum when t plus equals to 0. So this minimum of the waist is when t plus equals, when t equals minus z. And that more or less describes the behavior of this beam. So now what we did was to find solutions which would not have the deficiencies of Bessel beams and the deficiency of Laguerre-Gauss beams. And we call it an exponential wave. Why exponential? Because the dependence on rho is mostly exponential. It's not a Gauss function, but it's just a plane exponent. Since h of rho and t for large rho is linear in rho, therefore the fall off is not as fast as it was before. The dependence on time occurs in various places, and it is not obvious that this wave does not propagate in both directions like we noticed for the Laguerre-Gauss beams. And this will be explained in a moment, that this wave indeed propagates only in the positive direction. Now, what else do we have here? Of course, this factor e to the I L phi, because we need this factor to describe orbital angular momentum. And looks quite complicated. How did we arrive at this complicated solution? Well, we did it before in optics, and one of my main tools how to do physics is to look into Rizик and Grotstein. So this was obtained by Rizik and Grotstein, which will be seen on the... We needed badly a solution, and we knew that Bessel beams are good solutions, so why not use Bessel beams as building blocks? Instead of trying to decompose solutions into plane waves, we use a different complete set of functions, Bessel functions. And from Bessel functions, one looks into Grotstein and Rizik, and one then can find that in various cases this integral can be done analytically. And this is one of those cases. This function here, which depends on the parallel energy, so to speak, which is the amount of energy which is carried in the direction of propagation. And so this is a wave packet, and the integration has the meaning that, of course, it's spread in frequency. However, here we have this control factor. If B is large, then the spread is rather small. I will illustrate this on the next slide. And this is the Bessel function that we had before of this argument. What is this argument? It's the same as before, is the transverse momentum, because it's the difference because full energy and the energy in the propagation, so that's the same factor. And this important factor here clearly indicates that the wave is propagating in one direction, provided Pz is positive, and of course E is positive because we describe electrons and not positrons, which means that the frequency must be positive. So this proves that the wave propagates only in one direction, and there are no back propagating waves. So this is a solution of Klein-Gordon equation. Now we can see even better, since it's a combination of the solutions of Bessel type, which are solutions one can easily check. It is much easier to proceed through this than to check that this is a solution of Klein-Gordon.
PZ is a function of energy, and this...
No. PZ here is fixed. It's a parameter.
It is a parameter.
Yes.
You can take it out from this integral totally. Look at
Yeah.
Look at the formula.
Okay.
That's right, yes. Okay, so now let's go back to physics, to the Dirac equation. First, a side remark here about the behavior of this beam. Parameter B here must be large. And why it must be large? Because otherwise, if B is small, then the wave will be extending too far, and it must be very large as compared to what? As compared to the Compton wavelength here, which is the parameter that fixes the scale. So, as I already mentioned, the exponential solutions are labeled by two quantum numbers, Pz and L. And in addition, we have this dimensionless parameter B, which labels different solutions. Now, my side remark about the properties of these beams as functions of B. Now, this is the cross-section of the beam. The beam, of course, has cylindrical symmetry. Now, this is a cut. This is the axis. And this, of course, must be zero at the origin, because these waves have angular momentum. Therefore, Bessel functions vanish at the argument equal to 0. And as you increase B, the wave becomes much more spread in the radial direction. When you take B small, then the wave becomes more concentrated. You see, this wave is like a tube. Of course, Bessel functions have this property. They vanish at the origin, and then they have a maximum, and they fall off. Of course, ordinary Bessel functions have oscillations. These exponential beams do not have any oscillation. They just drop off exponentially. Now, this is the behavior of the modulus of this function as a function of rho. Now,
So it's not a beam cube.
it's a beam in the form of a tube. Why tube is not a beam? It runs, the tube runs in the z direction.
Is it just simple linear scaling?
No, it's not simple. It's non-linear. However, as you see, this is not a straight line. There's some curvature here when you would join the maximum. Now let's look at this wave from the other point of view, from the spectral point of view. What is the spectrum here of this beam as a function of the energy? And the spectrum, of course, has the opposite behavior. If beam is concentrated, if B is small, then the spectrum, of course, is diffused. When the beam becomes spread in coordinate space, then the spectrum becomes more narrow. That's the uncertainty principle, and it's nice to see the uncertainty principle realized in this case. Now, we go back to the Dirac equation now, because this is something completely different than what we saw in the non-relativistic case. It's the spin-orbit coupling. And let's illustrate this in the simplest case of Bessel beams. Other beams have the same property. The full Dirac B-spinner here has 4 components. Of course, I use the simple case when only the upper part is populated. One could do it more generally. What is important is that there is a combination of solutions with L, and in addition there is a solution with L plus 1 of this Klein-Gordon equation. It must be there. I will show you a proof in a moment that every solution of the Dirac equation must have parts which cannot be an eigenfunction of orbital angular momentum. And that creates a lot of problems, because when one discussing vortex lines, for example, the wave must have a phase which properly behaves, and that can happen only if it has one phase, not two separate phases. This solution has e to the IL plus 1 phi, and this solution has e to the IL phi. So this is what happens. However, this solution, in spite of having two different values of L, is an eigenfunction of the total angular momentum. And that has already been noticed by Dirac in his first paper, that the properties as far as the angular momentum goes for relativistic electrons are completely different from non-relativistic case, because in the non-relativistic case there is absolutely no coupling. You find a solution of the Schrödinger equation without spin, and then you multiply the solution by a spin factor, and they are completely different, and you can combine them the way you wish. You cannot do it in this case. There is spin orbit coupling, and the proof of this fact that you cannot have solution is quite simple. You take the Dirac equation here, written here. Next, you assume that it is an eigenfunction of orbital angular momentum. That means that you can multiply this solution by orbital angular momentum and use this fact. However, you cannot just commute orbital angular momentum with this part here, because electrons have spin. Therefore, it's only the total angular momentum that commutes with the Hamiltonian. And using this argument, one finds that the condition that the wave function psi is an eigenfunction of Lz is simply that H must commute with the Hamiltonian, at least acting on this wave function. Not in general, but acting on this function. Now if this is true, then you take the square of this acting on psi, and it must be also true. Now what is the commutator? The commutator is some combination of gamma matrices and whatever. When you calculate the square, it turns out that this is nothing else but the momentum in the transverse direction. Now this equation here has no physical solutions, because they either blow up at infinity or they blow up at the origin. Therefore, there are no regular solutions of the Dirac equation that are eigenfunctions of orbital angular momentum. What does that mean in terms of vortex lines? Well, we have a problem, because if it's not an eigenfunction of L, the normal analysis of vortex lines does not work. How does normal analysis of vortex lines in quantum physics works? We take the wave function, and then we take the following combination. Take nabla psi, and we subtract from here psi star and nabla acting here, I times psi, and then we divide this by the density, and if you wish, one can also multiply by h over m, and then in the numerator one has the velocity, and of course to have a vortex line, if the velocity has a curve, if it has the vortex structure, then it must vanish, the density must vanish at the origin, and that's quite simple in the Schrödinger case. However, here you cannot do it because psi has 4 components, so they cannot vanish all at the same time, and that creates a complication which shows that the notion of vortex lines is subtle in the Dirac case. Well, there is one way of formally doing this. Instead of taking the velocity as this object, which is usually what is done, because when multiplied by the charge, that becomes the current, and we know that current is the velocity times density. So that is the physical definition of velocity, and this definition does not work. What one can do is to extend this to the Dirac function. However, it's not clear what kind of measurement would measure this object instead of measuring the current, which is the property of the Dirac equation. Oh, I think I finished before time, so I hope there will be some questions.
These vortex lines are defined only for scalar function.
No, they can, oh, no. I have to go back, how many, 2 or 3 years when we defined vortex lines for the electromagnetic waves.
This I understand, but there was a specific trick which was used there, because a priori vortex means that the phase of a
Yes.
function is not.
Yes. So perhaps this is something worth considering. Maybe we will try to do it, to proceed the same way we proceeded in the electromagnetic case. What we did then, I can remind those who were not present at my talk, namely, there is something which I call the Riemann-Zilberstein vector. It's a complex description of electromagnetic field, and if you take f squared, then you have one scalar function, and the phase of this one scalar function can be used to define vortex lines, and they do exist, and one can draw them, and they of course evolve in time, etc. And here perhaps something similar can also be done to find some interesting scalar function which would still have the phase, so it cannot be psi bar psi.
Incompressible fluid, where the notion of vortexes emerged, the same problem is because the density is constant and the vortices do exist, so the energy becomes infinite at the center. And somehow the things to fly and
Yes, no.
are occasionally
Okay.
fly.
Of course, that is because hydrodynamics is not fundamental physics. We know that when we get closer and closer to the vortex, we lose. Yes, and the core. We have the core, and here we
There
have,
is a core here.
due to gravity. I don't know, maybe
Due to something.
due to something. Yes,
Some fundamental structure.
that's right. Yes.
Something is so. I mean,
But that's the next step. But clearly, the Dirac equation is more fundamental than hydrodynamic equations.
The description of vortices have not been rejected to this view, and
Yes.
the solution was found by looking deeper
Yeah,
to
yeah.
the microscopic structure.
That there is a
And
core.
What prevents us from thinking that the Dirac equation is just, I apologize for using the word, hydrodynamic.
Of course, this.
Hydrodynamic description. description, right?
But of course, these problems would arise also in what Mariusz Gajda is, for example, doing with other collaborators, namely, Gross-Pitayevsky equation is fine, but it's a phenomenological equation. When you get closer, atomic structure becomes important.
The Gross-Pitayevsky has a finite atomic core. There's no problem with vortices.
No, vortices are.
Yeah, but they have a finite density at the center. There are solutions, vortices.
No. No.
Why? There is
No,
a structure.
here we have an expert. Who shakes his head this way, and he's not Chinese.
But there is, of course, there is a shape of the vortex core that you can solve.
When you have vortex, the density vanishes.
The density vanishes, but it's not singular. The question here is
What?
the
Velocity is singular.
No, the question is that there is no point of discussing. The velocity might go up, assuming that the density at the center goes to zero.
Yes,
Properly.
yeah.
So the current, mass current is growing up. And that is beautifully described by the Gross-Pitayevsky. Okay?
Yes.
Then you should shake the hands in the proper
The same
direction.
is with
Not in the direction. I assume
The
you
same is with Schrödinger equation.
the same is
If you take
then there's no difference.
no difference at all.
I mean, the function f is different, the shape is slightly different, but that's
We're
irrelevant.
talking about Schrödinger equation.
Okay.
For electron and hydrogen atom with angular momentum.
Okay, any other remarks or questions? I don't see.
I think it's a physical, I mean, that's the way you think it is.
Okay.